Right. Welcome back to the session. It's been a while. So now in this video or session, we are actually going to discuss the application of first ordinary differential equations as much as we have learned the techniques of integration. So now the first application of first ordinary differential equations, we're going to talk about the population growth. We're going to look at population growth. This application of mathematics is wide, broad, it's wide range. More especially can refer to it as under this, if you are a microbiologist, this is one of the mathematical model or concept that you can actually utilize to work out through your field, whatever. So now application number 2 is called the radioactive decay. It's also referred to it is also referred to as exponential decay. This is also a wide, flexible application of mathematics. And then number 3, we're going to talk about the Newton's law of cooling. This one is highly applicable in chemical engineering. We're going to talk about the transfer of heat, transfer of energy from high state to low state. When we talk about cooling, it's when we expect the temperature to decrease of a certain surface from high temperature to low temperature. It's very high applicable in my chemical engineering course. And therefore, number 4, we're going to talk about the mixing problems. The mixing problems, it is also very high under the application of the chemical engineering course, where we're talking about the flow rates of the fluid in a tank, certain source of pipe, mass flow rate of that fluid in a tank or out of a tank, and so forth. So this is also highly applicable in my chemical engineering field. And then we have the last application that we're going to do, which is called the electrical circuits. It explains itself, electrical circuits, meaning this is highly applicable in electrical engineering and so forth. But for sure, these applications, they are not only focused on those courses that I have just mentioned. Could be applicable in civil, could be applicable in industrial, polymer, and so forth. Okay, so these are the applications. We have learned the techniques. We have seen how does the techniques actually work. Variable separable, homogeneous first order, linear first order, and Bernoulli. My spelling there is all. And Bernoulli. We've seen on how to apply these techniques. So doing these applications, we're gonna apply the very same techniques that we have just learned. Okay, still gonna repeat the same thing over and over and over again. And then after talking about the applications, most definitely we're gonna jump to the numerical methods, where we're gonna determine the general solution of differential equation using numerical methods, applying it by Euler's rule or Euler's method, and you will see how we do that. Then I think there are numerous methods. I don't know, many different methods out there. I haven't looked much of onto it. Just looking for this one that we are doing, the Euler's method to determine the solution of, and then to do the approximation and so on. You'll see how we use the numerical methods. Okay. All right. Right now, let's have a look at the applications then. Number 1, as we mentioned, let me do this, my pen. Number 1, as we mentioned, we're gonna start with the population growth, right? Which is also referred to the exponential growth. What is population growth? Population growth refers to a growing population over a period of time, right? This depends on time. This is 2024. What will be the population growth in 2050? So we can see that there is a time involved within that interval of 2024 and 2050, meaning there is a time period. Okay, so we want to talk about the population growth within that time period. That's why I'm saying this population growth application, it is very, very, very wide under the application, can be applied in many different fields. Like I said, even the microbiologists, they apply this, and I think mathematicians say, or microbiologists, they say this is more accurate under the small organisms that are continuously growing. For example, the bacteria. Ne? Microbiologists will tell you this, that the bacteria, they reproduced at a larger rate. For example, when you go at the feast, this feasts, ceremonies at home, and then you eat the meat, then the meat has bacteria and all of that. And when you consume that meat in your stomach, the bacteria, they continuously go in your stomach. So they grow within a short period of time. You understand what I'm saying? So using this application or this model of mathematics, it's highly accurate when it comes to situations like that. So now here, when we put this in words, when we talk about the population growth under mathematics, we're going to be too much on theory. We're just going to say the rate at which population grows is proportional to the total number n at time t, which is true. Rate simply refers to time. So meaning the rate at which population growth, meaning the time at which this population growth, it is proportional to the total population. Meaning if time continues to go higher and higher, meaning we're gonna get more population. But if time decreases, that means you're gonna get lesser population. But we know that time doesn't decrease, time will always move high, will always move up. So that's why here we're talking about the population growth and so forth. There is a decay, but you will see how does the decay actually works, okay? So here when we talk about the population growth, we're talking about that in respect to time. So what we just put here in words, we can represent it again in a form of mathematics. So using this equation over here that has proportionality sign, we can say dn over dt, dn over dt, this is ordinary differential equation, is proportional to n. So this simply means that dn over dt, it is the rate at which population growth, it is proportional to the total population at time t, okay? So if we want to formulate the equation without the proportionality sign, we're going to have to introduce the constant k. So here we have dn over dt. Now we change the proportionality sign into the equation, and then we introduce the constant, which is called constant k, okay, multiply by n. Now the equation can be, it's fine, you can represent your equation in different ways of differentiation. You can represent it as dn over dt is equals to k multiplied by n, or you can say your n prime with function t is equals to k multiplied by n at t. Okay, we can also do it in this way. It is still fine. Now, from the very same equation, which is dn over dt is equals to, from the very same equation, which is dn over dt is equals to k multiplied by n. If we want to solve for n, or we want to make n subject to the formula, by determining the general solution, this is the differential equation, and then we want to determine the general solution, which is the general equation, okay? So how are we going to do that? So let's determine the general solution using the techniques that we have employed. But firstly, we're going to have to determine which technique are we going to use. Are we going to use homogeneous? Are we going to use Bernoulli? Are we going to use first linear differential? Are we going to use the separable? Okay, we want to check which technique are we actually going to use to determine the general solution of this differential equation. So now here we have a differential equation. We can see that this will lead to a standard form of homogeneous, but definitely homogeneous will fail at this point in time because we don't have homogeneous equation at the top and at the bottom. And you know how to spot whether this is homogeneous or not. You look at the degree of the function at the top and the degree of the function at the bottom. So in this case, we have kn over 1. So we have kn over 1. That means we can't talk about homogeneous. It fails. So now let's try to separate these derivatives with respect to the dt and dn. So to separate this together, we're going to divide the whole equation by n so that we group with dn. So we're going to have 1 over n multiplied by dn, which is actually equals to, we take dt on this side by cross multiplying with k, we're going to have k multiplied by dt. Now, let's have a look at this side. We have 1 over n multiplied by dn. It's nice because we can see the variable, it goes with derivative n, and this side we have k, which is just a constant. It doesn't make any harm. We can just leave it there, and therefore dt. So we can see that the separable, it is the one technique that is actually going to work under the population growth. So now what we do then, we integrate, because we are using the separable method. So we're going to integrate both sides of the equation. And then what is the derivative of 1 over n multiplied by dn? It's going to be ln of n. Okay, it's going to be ln of n. And on this side of the equation, what is the integral of k multiplied? K is the constant, we take it out, there it is. And then dt, we bring t back, right? Because we the derivative of 1 dt, we bring t back. Therefore, plus c, which is our constant. Now remember, the objective of this method, of this whole idea, is to make n subject of the formula. But look, n, it is represented in a natural log, so we're going to have to extract that n, right? We want to express our answer explicitly, not implicitly, so that means you're going to have to solve for n. So to get rid of ln, we're going to have to introduce e. But remember, what we do on this side of the equation, we're supposed to do it on the other side of the equation. And therefore, e to the power of ln n, it will give us n, which is what we are looking for, positive. And therefore, what's happening on this side, we don't care, but we know that we can just separate this, reversing the laws of exponents by just separating these exponents together like this. So you can represent your answer again in this form, and as the function of t. That's population growth. Now, referring to population growth, like I said, this is a standard form. Okay, always know that for population growth, we use this standard form. dn over t is equals to k multiplied by n. So like I said, for population growth, it's highly accurate in predicting population growth in small animals and bacteria over short periods of time, which is what I have just explained right at the beginning. And then too simplified for humans and large animals. So this is too simplified for humans and large animals: predation, war, natural disasters, and viruses. So this is too simplified for humans and large animals. So it's fairly accurate when we talk about small animals or small organisms, such as bacteria and so forth. And then now here, I want us to talk about the radioactive. But before we talk about the radioactive, let's go to the question of population growth. All right, then, so now here's the question, example number 1, the application of population growth. Now the question says to us, a bacteria culture initially has n naught number of bacteria at time 1 hour. At time t 1 hour, the number of bacteria is measured to be 3 over 2 n naught if the rate of growth is proportional to the number of bacteria at nt present at any time. Determine the time necessary for the bacteria to triple. So now let's just break this down so that we can understand how to solve this question. So for a fact that here we are talking about the growth of bacteria and so forth. So that means we are talking about the population growth. Now, the first thing that comes in your mind before you solve the question, you need to, from the statement, you need to understand which application am I actually working with. I'm working with population because it's bacteria growing. So in this case, the standard form, which is not good, you're not going to be told, you need to figure it out by yourself. The standard form, the population growth, we know that it's going to be dt over, sorry, dn over dt is equals to k multiplied by n. This is what you need to figure by yourself. It's population growth, and this is standard form for population growth. Now, the next thing that comes is we are actually given the conditions. Remember, when we were doing the techniques, We have the differential equation. We solve that differential equation to get the general solution. Sometimes they will give us a differential equation and the conditions so that we can get the particular solution. So in this case, we check, are we given the conditions? Yes, we are given the conditions. Now, where are the conditions? They say a bacterial culture initially has an O number of bacteria. So we are not given the exact number of initial bacteria. We're just given maybe they could be 200. So these 200 represent an O, but it's initial. And be careful because here we are talking about two functions, which is the number, two variables, which is the number of bacteria and the time. So if you are given number of bacteria, what's the time of that number of bacteria? Initially, the time is 0 because we haven't started anything. We haven't seen the growth or the development of bacteria. So at this point in time, the time is 0 initially, right? Because we are about to start things. We are about to start to see the growth of bacteria. So how many bacteria were there initially? We say maybe there were 200, and O means 200, right? Okay, let me do it like this. I want to start with time first. Let me do this. So how many bacteria were actually given at what time? At number of bacteria at the time 0, 0 hours, we had 200 bacteria, right? Same as f of x is equals to x squared. You will say f at 0 will actually be equals to f at 0, which is 0 to the power of 2. So here, this is not the 0 thing, it's just the number of bacteria. Maybe at time 0 hours, we had 200 bacteria. Before we could see at time, before we start the time of growth to track that growth of bacteria, maybe we had 200 bacteria. And in 1 hour, in 1 hour time, now the number of bacteria has measured to be 3 over 2. The number of what? At 1 hour, the number of bacteria at 1 hour, they were measured to be 3 over 2 of n naught. So this n naught means it could be 200. Maybe if initially our bacteria were 200, so you're going to say 200 multiplied by 3 over 2, and then we get 300. So meaning 1 hour later, the number of bacteria, they're going to be 300, if maybe initial, but we don't know the exact number of initial number of bacteria. So we're going to represent that as n naught. I hope you understand what I'm doing here, okay? So another condition, this is two conditions that are provided for this differential equation, okay? How did we get this differential equation? Population growth. How did we get these conditions? We were told initially we had, which is 0 hours, we had n number of bacteria, and then at t1 hour, the number of bacteria measured to be 3 over 2 of the initial number of bacteria. If the rate of growth is proportional to the bacteria according to this equation, present at any time, therefore determine the number of determine the time necessary for the bacteria to triple. So what we want is we want to know at what time, right, and t, at what time did the bacteria triple, but which bacteria tripled? They tripled. So the initial number of bacteria, they actually tripled. So we need to determine the time when the bacteria triple, right? From 200, it's going to be 600. If they triple, it's going to be 2 for 6 years, it's going to be 600, right? If they triple. So these are the conditions, and this is the question where we want to determine time. So now let's work with the equation then. Firstly, what are we going to do? We're going to determine the general solution. So which technique are we going to use? Let's see, we have dn over homogeneous fields. That means we're going to have dn multiplied by 1 over n when we take n to that side by dividing both sides by n. And then this side, you're going to have k multiplied by the dt. And then we integrate both sides because you can see this is separable, right? So here we're gonna have ln of n, which will be equals to k multiplied by t plus c. So what we get over here, it is the general solution from this differential equation. But we were given the initial condition. So at time 0, we get this number of bacteria. So that means where we see n, we most definitely going to substitute n naught. So in this case, you're going to have ln of n naught. We use the condition n at 0 is equals to n naught at this point in time. So when we substitute 0 over there, it's going to be 0, and then we're going to left with c. So that means c is equals to this. Now, the reason why we use these conditions, like we have the general solution, we need to determine the constant first before we can determine the answer. So we need to know the value of k in terms of n and k. If that's the case, we need to know the value of c in terms of k and n naught if that's the case. So already we determined the value of c, and then we're going to do a back substitution. So we're going to substitute this equation onto this equation. So where we see c, we're going to write this. So on this side of the equation, we have ln n is equals to k multiplied by t plus ln of n naught. Right. So now we still have our constant, which is k. Everything is fine, but the problem is our constant k, right? So now, how are we going to eliminate that constant k in this case? Now, in order for us to actually eliminate our constant k, now this is what we're going to do. We're going to use the second condition, which says n at 1 hour. It will be 3 over 2 n naught. So here, we're going to substitute 3 over 2 n naught. So we're going to have ln of 3 over 2 n naught is equals to k. Remember, at 1 hour, we substitute 1 over there. Plus, we're going to write everything as it is, ln n naught. And therefore, from here, what we're going to do is, remember, we want to solve for k, right? So we're going to transpose this on the other side of the equation. We're going to have ln 3 over 2 n naught subtract ln n naught. What is k multiplied by 1? It's actually going to give us k. And therefore, remember, according to laws of natural logs, we know when we subtract, we can just divide. So that means here we're going to have ln 3 over 2 n naught divided by n naught will be equals to k, right? This is the law of logs. This cancels that. And then on this side, you're going to have ln of 3 over 2 is equals to k. Now this is the constant k. Constant k is equals to ln of 3 over 2. Now we can substitute k, we can substitute c onto this equation. And then we have the particular solution. Now, after having that particular solution, I don't want to waste time and write it as a, okay, it's fine, let's write it. So meaning our particular solution in this case is going to be ln n is equals to our k. It's going to be ln of 3 over 2, which is our k, and then multiply by t, plus our c, we said it's ln, it's t, plus ln of this over there. So at this point in time, we have the particular solution. Now we use the particular solution to solve for our question. So they wanted us to determine ln at, n at t is equals to 3n. So we needed to determine time at this point in time, right? So n at t in this case is 3n, right? We have 3n over there. So that means what you're gonna do is we have ln 3 NO is equals to ln of 3 over 2 multiplied by T plus ln of, oh, remember T is what you're looking for. That's why I left it as it is, ln of NO. Therefore, take this on the other side. We're going to have ln of 3. When we take this, we group it with that, just like how I showed you over there. We're going to have ln 3 over 2. And then here we're going to have ln of 3 over 2 multiplied by T. And then we divide both sides by ln of 3 over 2. Therefore, our time will be how much? Let's do it. We're going to say ln of 3 divided by ln of 3 over 2 on my calculator. And then I get 2,70952 to 2 decimal places. I'm going to have 2,71 hours, okay? Because remember our time, it is represented in hours. And therefore this will be our final answer to this, okay? That's how we deal with population growth.